So my thought was this time maybe we would talk about some of the basics, and some of the stuff we probably didn't actually talk about in the first couple of weeks either. If anyone has stuff they want to talk about, questions to ask or anything like that, we can start with that, because I don't have like a real major agenda with the other sort of thing. I just thought I'd cover some sort of general purpose image processing and format conversion and metadata and that sort of stuff a little bit. What were you asking, Eric?
Yeah, I mean, so just if there's you showed a great workflow of how to just make like a sphere in the last talk. If there's a way to, and I understand it could be more complicated, but if there's just a way to make regularly spaced lines of X pixel dimensions, and yeah, because like
there is no standard method for drawing lines or circles or boxes or something like that on images in EMAN2. That's it's not the sort of thing that you really need to do as part. There's annotation tools. So if you're displaying something in a 2D image, you can put annotations on top of it and stuff. But there's no way of actually drawing into the image with some pre-existing function. So you have to use a for loop.
Okay.
And if you're going to be doing it thousands and thousands of times, then it should probably get implemented as a processor, like that Helix filter that we wrote, which is basically doing exactly what you're describing, just in Fourier space, not real space. But if it's something you're just doing a couple of times, you can just do it from Python and it'll be fine.
Okay. Okay.
Let me run a Jupyter Lab session. We'll do it from that. All right. Oh, got a terminal session. That's interesting. That's not what I intended. All right. Anyone else? Any questions you want to ask before we start doing other stuff? All right. Let's go to sort of basic fundamentals and talk about EMData objects and how it's different than a NumPy array, and how to properly do I/O and that kind of thing. So you're probably all aware at this point that EMData is the basic class for images in EMAN2, and this dates back to the late 90s or something like that. I mean, this class derived from a class that was written in the very early versions of EMAN1. So this class has been around for a long time. We've just made various improvements and changes to it, including making lots of things modular and having a better header associated with it and stuff like that. So the original EMAN1 version of it had a fixed header variables that were associated with it. Now in EMAN2 there's arbitrary metadata that you can associate with it, but basically you've got the EMData object. So we'll say from EMAN2 import star, and well, we'll go ahead and do that. Then let's make an EMData object. So you can just do this, of course, EMData, and that will make an empty EMData object. And if you want the dimensions, it's a 0 by 0, I think, probably object. So it's a really empty 0-sized EMData object if you do it that way. So not very useful. Now you can do stuff with it. So once you've created that, if you want to read an image, you can say a.read. Actually, I don't know if I have any images in this local folder. Let's see. Oh, that's not what I meant to do.
I could email you some line images. Okay, I'm just kidding.
Yeah. Okay. So I have nothing in this folder. So we're gonna make a test image first, and this just makes a standard sort of S-shaped test image. and then we're going to write that to a file. So we'll write it to just an HDF file for now.
Test image is a function?
Test image is a built-in function which will make various types of 2D test images. So you can see the different types. Oh, sorry. Basically that was the help on the EMData object because it was, there we go. If you don't call it with anything, it returns this sort of S-curve kind of thing that has a lot of texture inside it. It's a general purpose test image that it has handedness, it has lots of different spatial frequencies in it, so it's just kind of a generic useful test image. But then there are other types of test images you can create. You can also specify size if you want the default's 128 by 128. So we will just write that to a file, and that'll give us a file that we can play with. There's also a test image 3D, which has different sets of things, but it'll return 128 cubed volumes. I guess we might as well go ahead and make one of those too. Let's make, the axes aren't very useful. Maybe an ellipse with holes. Let's see, Gaussian ellipsoids, 3 axes different. Let's make a type 7 test, 3D test image, and we'll call that y.hdf. So if we go to our terminal, yeah, we should see that we've got an x.hdf and a y.hdf. All right, so one thing at a time. So let's start with just the image object itself. So if we make an EMData object like this, it's just completely empty. It has 0 size. It's not useful. We can say a.read read image x.hdf, and then that will overwrite the current image basically with whatever the contents of that file are. So now if I do a of nx or ny or nz, it'll give me the dimensions of the image object. This will work with any file type that EMAN recognizes. There are a bunch of options here, and we'll look at the options in a minute. But you can just call it on a file like that, and it will read the first image from the file. If it's a stack or something like that, just into memory. There's a shortcut notation which we've used in previous sessions where you can just say EMData and use it as an initializer for the EMData object as well. But basically what that's doing is calling EMData, and then it's calling read image when you do it that way. So it's equivalent, but it saves you the step of creating the image first. Oops, a equals like that. So that it's basically exactly the same. Although the read image function has maybe a few more options to it than you get when you call it using this strategy. Now the image file that I just created was just a single image in a file. So maybe we should go ahead and rectify that. I will. Let me think. I think I may actually have some interesting.
I know this is an easy documentation question, but something I'm going to look up later, so I figure I'll just ask here.
Go ahead, ask the question.
Can it read PNGs? Like can you make an EMData object out of like a PNG and a JPEG, or does it have to be?
Yes and no. Yes, you can read a PNG, but if it's color, you're not going to get any color. It's going to interpret the color in some fashion or something like that. So, if you look, so if we want to look at, let's see, let's make a new tab. All right, so if we go to the EMAN documentation, the things you need to know /fact section is where most of the interesting stuff lives now. Probably should rearrange it again, but anyway. And one of the things here is file formats. So this is a complete list of all the image file formats that EMAN currently supports. And it'll tell you whether you can read them and or write to them, whether it supports 3D volumes, whether it supports stacks of images, whether it supports stacks of volumes, whether it supports bit truncated writing, so this is compression without the actual compression, and whether it supports reading just part of the image in, or whether you have to read the entire image at once. So for each format, it documents whether it supports those things. So these are the top are sort of the cryo-EM file formats. That if we go down here, you'll see standard non-cryo-EM formats like PNG. So PNG you can read to, and you can read from and write to, but it doesn't support stacks and it doesn't support volumes. PGM is another standard format. JPEG, you'll note, you can you can write to JPEGs, but you can't read from JPEGs. And that was something that was done intentionally, although I think we're going back and we're enabling that now. Just because after doing all that testing as part of the compression paper, JPEG files can be used. It's not a good idea. We wouldn't encourage it, but if someone has a JPEG file and they want to read it, we don't want to stop them from doing it entirely. Anyway, so these are all of the supported file formats and all of the various options that are supported for each one. And anytime someone says, oh, hey, there's this new file format X we'd like to support, as long as we can find the documentation to let us support it, we'll do it. Some of the file formats that we support, for example, are like these DM2, 3, and 4, which are proprietary file formats from Gatan, where they don't want to provide any documentation to people, because then they feel if they've done that, then they can't make changes to the file format themselves as flexibly. If they control it completely internally, then they can change it whenever they want, and they don't have to worry about it. But through looking at the file format, you can actually sort of reverse engineer it and figure out how it's assembled, and we've done that for these different file format types. And we did get a little information from Gatan to help us out on that. They're not. The reason they don't make it public is just a practical reason, not a legal reason. So they're not adverse to people knowing. They just don't want people. They don't want to feel responsible. EER is actually documented. That's been added. Although this one is a little bit complicated, right? Because the file format makes it seem like you've got 1,000 frames per second, or some ungodly number of frames per second. And then you just have a handful of pixels in each of the individual frames. So to do anything practical with these frames, you pretty much have to do some level of frame averaging. So dealing with EER files has sort of its own set of issues. All right, anyway, I didn't mean to spend all that much time on this. So EMAN supports all...
Sorry.
No, good.
Can I ask about TIFF stacks?
Yeah.
Are
TIFF
those...
stacks, you should be able to read from TIFF stacks, I think. It says no here, but
I think I tried also. I don't know.
You tried and it doesn't work?
Yeah, because you get TIFF stacks. I just for the heck of it, I tried, but I don't know if I would. Yeah, maybe because you get TIFF stacks out from the fluorescent camera, and I was just for the heck of it was like, hey, let me try to read these.
Okay.
Yeah, that's also the only way to write movies from Serial EM with compression right now.
Yeah, no. I realize that. No, it's a standard format. I could have sworn we added support for reading TIFF stacks. I thought we just hadn't added support yet for writing to TIFF stacks. I mean, TIFF is actually
tried, so I'll try it.
Have you tried? You haven't tried it.
No, I just looked on the table.
Oh, okay. So one of the issues is getting the people who actually do the updates to update the documentation, which unfortunately doesn't always happen. Let me just take a look. I think I'm sure I have. Oh, actually, on this machine, I may not have any TIFF files here. Yeah, give it a try. And
yeah, I have a million of them.
Yeah. Our intention is to actually support writing to TIFF stacks as well, but we haven't gotten around to doing that. The problem with the TIFF file format, I mean, in many ways, TIFF would be a reasonable alternative to HDF. The one way in which TIFF is not a reasonable alternative is that it uses 32-bit pointers internally everywhere, which means that the size of a single TIFF stack is limited to 2 gigabytes, or maybe it's 8 gigabytes if they did it a particular way. But anyway, it's limited in size. So you can't make really big TIFF files unless you use the alternative big TIFF format, which uses 64-bit pointers, which would make it very suitable, except for the fact that almost no one supports big TIFF for anything.
I have a hard drive with TIFFs on it. I don't know if you want to do this now, but I could give it to you.
You are welcome to. I have plenty of TIFF files. I just don't have them on this computer.
No, I'm saying I have one with me right now. I'm in the lab.
Well, that's fine. You can test it right now if you'd like.
Okay. Yeah, okay.
But I don't want to take the time to copy one right now.
Agreed.
That's all. I'm pretty sure that we support TIFF reading already, but I haven't done it in a little while, so I don't want to say it with absolute certainty. Right. So when you read from a file, it should be completely transparent. You should be able to say x.hdf or x.whatever, and it should be fine. And what I was looking for here is I thought I had some sample. Oh yeah, workshop samples. Let's see. I thought I had different file types there, but no, that's not actually very good. Oops. Where am I?
Yeah, it opens fine.
The TIFF stack's open fine?
Yep.
Okay, good. All right, so I'm going to go ahead and maybe I'll just completely change where I am. Just a second. Yeah, you probably cannot write to TIFF files still though. That's something on the to-do list. It just hasn't gotten done. And I guess I should update the wiki so it doesn't say that, or it does say that, however you want to look at it. In fact, I'm just going to do it right now so I don't forget. Of course, we've got to get back to the right page. Things you need to know. File formats. TIFF. Which one was it? Yes. All right, there we go. No inconsistency. Right. So if we look at this folder that we're in now, you can see I've got a sample, a magic image pair, and I've got a sample MRC volume, and I've got a sample spiders single image file and a sample spider stack file. I guess I don't have any MRCS files. So let's try this. I got to do this again. So spider stack, if I do that, I will just get the first image in the file. So another thing you can do is get attribute dictionary, which will give you the entire header of the image. And what you'll see if you read from a particular file type is you'll see all the standard metadata down here. So NX, NY, and Z, standard deviation, mean, angstrom per pixel, all that stuff. And then there will be file format specific header information up at the top here. And that's used both to give you access to it and to preserve the information if you write back to the same file format again. So if you write this file to an EMData object, sorry, to an HDF file, let's go ahead and do that. Let's say a.write image x.hdf, 0. Oops. I'm just saying 0 just to make sure it goes in as the first image in the file in case it already exists. And then B equals EMData x.hdf. You'll see that all that information gets preserved, right? So when you save stuff to the HDF format, anything that's stored in the header of the image, as it is in memory on the computer, will get written to the HDF file. If we save this to, say, an MRC file instead, it would only use metadata that was appropriate for MRC file. So if we go back here and we say x.mrc, oops, here, and say x.mrc, and then here we read from x.mrc, and then we look at the attribute header, we will see the MRC header stuff, but we will have lost the spider header stuff, right? If there was something in the spider header which got translated into one of the standard header items, and then that was compatible with one of the MRC header items, then it would have gotten written to the MRC header, but you won't find any of these spider header items. So when you write to HDF, that's the one file format which preserves all of the header information completely. Other file formats, it will only preserve stuff which is relevant to the format. And if we go back to the documentation here, you can see, again, it's under this things you need to know category. There's the image file format stuff here, and then there's the header information here. And then this lists, in theory, all of the tags that you might run across in the header, including the file format specific tags.
So you mentioned there was a white paper for storing the header information in HDF. If you get something that's not compliant with that white paper coming out of like an MRC or another format, does that just get shoved somewhere else so that it's not messing with, I guess, how the header information is supposed to be laid out?
So that not compatible in, you mean like there's a big chunk of binary data which can't be interpreted or something like that, or? I
guess does everything have
so
if there's header information in an MRC that doesn't have a spot in that HDF where it should go?
Yeah, it's true that for the MRC format, let's see what we might be missing there. I mean, you can see we do have the space group, and we have this number of characters used for storing symmetry operators, which is where that abused stuff in the header goes. But generally speaking, if you're reading one of the variants, like there's a separate header items for the FEI MRC variant, right, which has the a separate extended header. So if it's a file format which is MRC-like, but has some sort of, abuse of that extra header region, generally that will appear as a different file format in a certain sense, right? So yeah, I mean, we try and do a pretty good job of representing everything from the header, but the MRC file format is widely abused. I think we are covering everything that was documented in that last MRC file format standards paper from, what, 2014 or something like that. I was actually a co-author on that paper. I think we implement everything that was listed there in that paper, but if you find something that's missing that you need for some reason, tell us and we'll add it. It's really easy to add another header item if we didn't cover it. But you can see there's a lot of coverage for all of the different standard file types that we support. So we ask people if they're you can add any header item that you like if you're working with EMData objects. I can just like I can say A of NX. I can go the other way. I can say A of Steve is equal to 1, 2, 3, 4, 5. Oops. My typing.
So the reason why I'm asking is because I have MRC files that I'm trying to feed into some old Uppsala Software Factory programs, and they crash. And I've found that opening and saving the MRC file with Coot gets it so that it can read it. And I'm thinking I could probably figure out a way to sanitize
that
it
would,
with EMAN first.
EMAN would probably accomplish the same thing.
And I can script it. So.
Yeah. Anyway, I suspect that EMAN would accomplish the same thing. You'd have to look at the header to try and figure out exactly what's causing it to crash, and see. But yeah, the situation you're describing certainly isn't unique. Anyway, so so you can add arbitrary metadata to the header like that. I've added my own metadata item, and if I write it to an HDF file and read it back, that list of integers will be preserved. It's just that if you're going to do that sort of thing, that we encourage you to actually go and update yourself or ask us to update the wiki so it's listed as a documented header item that someone might use. Okay, so this is basic file reading and writing. I will point out that there's one exception for the other exception for the MRC file format. If the MRC file contains volume data, that volume data could either be a stack of 2D particles or it could be an actual volume. Ostensibly, there's a way of documenting that in the header of the MRC file, but it's a strategy which no one actually uses, or pretty much no one actually uses, so you can't actually trust it, which means that if you're reading from an MRC file, you can't assume that that is going to be present correctly. So we have followed Shore's footsteps in this respect, and if the file has a .mrcs extension, EMAN will treat it as a stack of 2D particles, and if it has a .mrc extension, it will treat it as a 3D volume. The actual contents of the file are identical in both cases, and if you write a volume to an MRC file, EMAN should generate an MRC file which has the correct header values set. It's just that on read, EMAN itself won't trust that header item because it's not trustworthy. So I guess what I'm saying is that's the one case in EMAN where the file extension actually matters. If it's MRCS, then it will be read as a 2D stack. If it's anything else and it's an MRC file, it will be read as a 3D volume. Now, if it's a 3D volume, if EMAN is reading something as a 3D volume and you want to read a slice from the volume, there's still a way of accomplishing that task. So let's see, we've got, I think we should have a volume. Yeah, here we've got an MRC volume. So let's read that volume in as a volume. Okay, so here's our MRC volume, and it's 100 by 100 by 100 pixels. And hopefully we've got reasonable values for everything else. So the angstrom per pixel value is set from the header. Obviously nonsensical in this case, but that's the value that came out of the values that were present in the header. We say, just so we know what we're working with, I know I could have done that via the EMAN2, the Jupyter session that we were doing, but anyway, so this is just an old GrowEL molecule. That's what's in that volume. So let's say we wanted to pull a slice out of that volume. How would we do that? So if we say help EMData read image, you'll see that it actually takes several additional parameters. You can give it an image number, so if it's a stack, and if it's an HDF file, it could be a stack of volumes. So if it's a stack file, you can tell it the image number. If you don't give it an image number, it'll read the first image by default. You can tell it to read the header only. This is particularly useful if you've got something like a 4K by 4K by 2K tomogram, and you don't want to read the entire thing into the memory of your computer, you can tell it to read only the header, and you'll still get an EMData object. It's just that the EMData object will only have header values. If you try to access any of the image data, it could even crash because it's just invalid data. But then you have this region option, which allows you to read a portion of the volume. So if we want to read a slice from that volume, and we know it's 100 by 100 by 100, we can say, let's see, image number, header, region, right? So there's no way of doing named parameters easily using the toolkit that we're using for passing Python parameters into C++. So you have to pass some value in for everything. So 0, 0, that's the header only flag, and then we pass in a region. And the region can be either a 2-dimensional region or a 3-dimensional region, depending on what your purpose is. In this case, we're going to make a 3-dimensional region, which would be, let's say, 0, 0, 10, and then 100, 100, 1. So that should read the 10th or the 11th, basically, slice of the volume. So it starts as x naught, y naught, z naught, and then x size, y size, z size. That's how you specify regions. So now if we look at the get attribute dictionary there, most of the MRC header is going to be the same because there isn't a separate header for that slice. But now if we look at the dimensions, you can see nx, ny, and z is going to be 1. And it will have pulled out a slice from the middle. The same option is available for writing images. So if you have a giant MRC volume on disk and you want to write just something to the middle of that image without perturbing the rest of it, you can read a slice out from the middle and you can write back to that same slice without having to read the entire volume into memory or something like that.
Sorry, can you explain again, why are you passing, you're passing 0, 0 before the region? Because
0 is the image number. This is whether you want to read the header or not. And that's because we don't have named, I can't say, region equals or something, I can't pass a named parameter in because it's not supported by the toolkit that we're using.
So you just have to pass something.
So you have to pass in something for all of the values. So you have to pass in the correct values, basically. Although I think if you pass none in, it will probably handle that properly.
Okay. So the zeros are real values, just
huh?
The zeros are real values.
Yeah, these zeros are real values because I don't want to. If I said 1 here, it would only read the header, and if I said 1 here, it would read the second image in the file.
Okay.
Let's see what else. Header only region is 3D can be used as a hint. So if that's another way you can kind of get around the MRC file format thing. So if it's a file format that only supports 3D volumes or 2D images, it doesn't support stacks directly. You can give it this hint and say that, oh, it's not supposed to be a volume, it's supposed to be a 2D image, and that may alter its behavior a little bit. You can also specify explicitly an image type if the header doesn't match the image type. So normally it's going to sort of try and use the header as a hint, and if it doesn't figure it out via the header, then it will sort of go through its list of all possible file types and try and figure out what kind of file it is. If you want to read explicitly one particular type, then you can specify it explicitly here. And let's see, yeah. So there's shortcuts here for all of the image types. So there's each of the different supported file formats here has an image underscore notation there that you can read out. You can specify there. The same thing exists for write image. So if we say help on write image, it also supports image. So image type occurs right near the beginning there. So file name, image number. So you can write to a particular image number in the file, and then image type is the next thing. So if you want to specify writing the header only, or you want to specify a region, and you want it to do the type automatically, that's where you could pass none in as the image type, and it should automatically pick the right type corresponding to the file name that you passed. Let's see. I should add, we talked a little bit about compression last week. That at the Python level, you can use this new notation and say something like :6 when you're writing to one of the supported file formats, and it will, oh, that's read image. Sorry, that's, I need to be doing a write. So let's say I have A and I want to write image. We'll write it to z.mrc. I can put a :8 there, and or a :6 there, and it will use only 6 bits for the data. So if we look there now, you can see that z.mrc is 100 by 100 pixels, because it was just a slice that we read out. So 100 times 100 is 10,000. So you can see this is a 1 byte format, right? So it's 8-bit image format. So let's just do this for fun. We'll call this z.mrc, and we'll call this y.mrc. So for y, I'm going to give it 8 bits instead of 6 bits. And now if you look at the two files, y and z are going to be exactly the same size because there's no actual compression. It just used a limited number of bits. But if we gzip y.mrc and z.mrc, all right, didn't make much of a difference in this case because it was mostly empty space. Almost everything in that image was 0, right? So it didn't actually take very much space at all. But you can see why, actually, why, all right, my demonstration didn't work. Let me do it on the whole volume. I want to actually do the demonstration. So, or let me do it with my noise data. We'll make a test image and do it. That'll work. That's what happens when you do demonstrations on the fly. Oh, sorry, y.mrc :8 and a.write image y.mrc z.mrc :4. Let's do one more. We'll overwrite my x.mrc. :12. I'll get rid of the GZ ones. All right, and now we can see that the x.mrc file is twice the size, basically, of the other two. These are 8-bit files, and this is a 16-bit file because you asked for 12 bits. And now if we gzip y.mrc and z.mrc, we'll find that the 4-bit file compressed a lot better than the 8-bit file because there are more 0 bits present in the pixels, so it's more compressible. So if you want to do file compression, but you don't want to use HDF format, you could use a compressed file system, right, where every file that you write to the file system is automatically compressed, and then you could write the files out with reduced bits, and you'd accomplish basically the same result. All right, so that's basic file I/O operations, and we covered a little bit about header values. So there are some limitations on the types of stuff you can put in the header. You can obviously put integers and floating point numbers and strings. Those are all completely valid. There are special objects. It supports transform objects. It supports other EMData objects as header values, and I think there's one other type of special object I'm not remembering off the top of my head that it supports. And then it supports lists of integers and lists of floating point numbers. So those are all things that you can set as header values. And if all else fails, you can always use a string and pickle something into the string or something if you can't come up with another strategy for saving it. But okay. Another important bit of infrastructure before I spend more time on images is actually these the JSON files that you find running all around EMAN projects and that sort of thing. So if we look at let me, oops, I'm not sure if these are already worked up. No. All right, here's a project. So if you look in this this project, you'll find that in the info folder, for example, there's a whole bunch of these JSON files. And associated with the JSON files are some, in some cases, there you'll find these JSON image files, which are in HDF format. In current versions of EMAN2, pretty much all of the metadata associated with image files, other than the header stuff, but metadata about a particular image that you want to preserve across different files and stuff like that, are stored in JSON files. If we look at one of these JSON files, of course, these are human readable files. It's a standard web format that's used in web programming a lot because it stands for JavaScript JavaScript object notation. That's what JSON stands for. So it's easily readable inside JavaScript applications and web browsers and stuff like that. But if you look at it, it really looks pretty much like Python, because JavaScript defines dictionaries using the same syntax, dictionaries and lists the same syntax that Python does. So the actual contents of these JSON files will basically be a dictionary, and then the dictionary will have a bunch of associated metadata items associated inside it. And these JavaScript files also support sort of arbitrary encapsulation of different object types the way EMAN does it. So there's an easy way of interacting with these files in EMAN. All you have to do is say, we'll call it JS, is equal to JS open dict, and give it the name of a JSON file. It doesn't have to be the info folder. It can be anywhere you like. And that will create a pseudo dictionary object in Python, which is a representation of the JSON file on disk. So let me go back where we were. Okay, so here's this test.json file that I just opened, right? If I look at it now, you can see it's empty. It just has a pair of curly braces. If I modify this file in a dictionary-like way, we'll find that is immediately reflected in the file. Okay, this is all handled in a way to be as thread safe as possible. So if you have a cluster and a bunch of different nodes are all simultaneously acting on these JSON files, you should be able to simultaneously open the JSON file on multiple nodes, and everything should be okay. It will lock the files correctly, so one node can't write at the same time as another node, and it uses temporary files and that sort of thing. So it's a very safe mechanism for storing metadata in files in a thread safe and in a parallel, a parallel cluster based way. The keys on the dictionaries in these JSON files have to be strings, but the values can be basically anything. If it doesn't have a built-in support for whatever it is you're trying to write to the file, then it will pickle it and it'll write it as a pickled string to the file. So you can basically put any kind of object in there. But if it's a standard data type, then it's easy. So I mean, I can say JS of def is equal to 1, 2, 3, 4, 5, like that, and that will also be fine. The other, EMData objects are a special case. So if I say A, and then say that's equal to test image. That's where these JSON image files come from. So originally, when we did this JSON stuff, we actually just embedded the image in the JSON file, but that produced these humongous text files, which weren't really very human readable anymore. So we changed the mechanism. So if you write an image to a JSON file, what it will do is put in a reference with this special __ image thing. So A here will have this special notation inside it, and then it'll point to the actual image object on disk. From a user perspective, though, I can then just say JS of A like that, oops, sorry, of A like that, and it'll read the image back in for me. Okay. We don't really encourage you to put image data directly in JSON files like this, but you can do it if you like. Most cases, it probably makes more sense to write your images to actual HDF files directly yourself, but you can do it this way. Let's see, anything else about these JSON files? From a documentation perspective, this is separate. So what we're looking at here are things that will be stored in the image headers. The parameters that might get stored in these JSON files in the info folders are separate. So here, there's another page. This stores the tags that we will normally use in those JSON files. And there aren't a tremendous number of those tags there right now, but anyway, that's there. All right. Maybe we'll finish off today with the one other place where you might find metadata stored. So metadata in EMAN2 has kind of evolved over the years. When we first came out with EMAN2, we did not use HDF files. We used BDB files. So we were actually storing everything, all image data and everything like that in these Berkeley database dictionary files. And the reason we did it was because when we first came out with EMAN2, which was in 2007, 2008, this was a beta version, or alpha version, the HDF file format had some problems. If you made HDF files with large numbers of images, not large images, but if you made an HDF file that had 10,000 images in it, it became impossibly slow. The guys who wrote HDF5 had never really sort of thought about the idea that people would want to not just put big volumes in, but they would want to put thousands of images in a single file, and they had not designed some aspects of the header with that in mind. So we complained to the HDF guys, and over the next 2 years or 3 years, they managed to sort of adapt things. So now HDF actually does support large numbers of images very effectively. But in that intervening time, of course, we continued with EMAN2. So we're using this BDB format for everything for a long time. This was terrible because you couldn't look at the BDB files directly. You had to interact with them with programs. So that meant that user who wanted to VI their file or something, they couldn't do it. And people found it really frustrating. And this was actually where EMAN1 was really widely used, right? I mean, it was at the time, it was the most widely used software in cryo-EM. And then when we came out with EMAN2, people hated the BDB stuff so much they started looking for alternatives at the time. So it was a big deal. Finally, when HDF started supporting things, we made a transition sometime around 2012, 2013, around the time RealIon came out. We finally kind of fixed that aspect of EMAN2 and started using HDF files and using JSON files for the metadata. So we started making another transition of sorts now as we're kind of moving towards EMAN3. We've always had, and this dates back to EMAN1, these LST files floating around. So if we look, let me go back to, yeah, we'll just do it here. I'm just going to go to a new project. I mean, a fair recent project, I guess is what I'm saying. Let's do this. So this is a project where I've been doing subtomogram averaging on yeast nuclear pore complexes. So if we look at some of these refinement folders now, with these new 2D and 3D refinement pipelines that are available in EMAN2, do an LS first. 7. You'll see that in each iteration of the refinement run, we get these LST files. And if you're doing subtomogram averaging, you actually find two different types. You may find 2D versions and 3D versions. But if you look at these LST files, so LST files historically in EMAN2 were used to avoid, used for a similar purpose to star files, in a sense. Well, not really. So star files are used to store metadata. In an EMAN2 project, if you look in, say, the particles folder or the tomograms folder, particles 3D, you'll see that particles are stored by micrograph, right? So this is a particular micrograph or a particular tomogram in this case, right? So this is one particular tomogram. Here's another particular tomogram, and or actually no, that's the same one. Sorry. So this is the name of a particular tomogram, and then for that tomogram, we've made different particles where we've done different things to the particles. You know, we've got some particles where we excluded certain tilts from the reconstruction. We've got other particles where we did dose weighting. So we've got different variants of the particles that may exist. So basically, we always keep the particles organized by tomogram or organized by micrograph, and they'll be so you know, you'll have a bunch of particles in this one file, and then we can have this double underscore notation. You may have variants of the file, something like that. But anyway, the point is that each image file only contains particles from one micrograph. That's the point I was trying to get to. And what that means is that you need to have these some mechanism for grouping together particles from many micrographs into a single file for processing. So in EMAN, we've got the sets folder, and the sets folder contains LST files. So if we look at sets host04.lst, what that will contain, it's a text file. It starts with a couple of special lines, commented out lines, but then it has basically image number and then file name. Image number, file name, image number, file name. So it's just a straightforward reference to another file. If you go into EMAN2 and you try to read from an LST file, it will treat the LST file as if it is an image file itself. In reality, it's a text file which references other files, but if I read the first image from this file, it will actually read this image. And if I read the second image from this file, it'll actually read this image. Now you say, well, why do you use this? Why don't you use, say, star files for that? Because star files are used by everyone else. Well, the one really nice thing that these LST files, or LSX files in this case, have is the fact that every line of the file is the same length. That length is 87 characters. What that means is if I want to read the 5,000th image from the file, I don't have to read the entire 500,000 particle text file in. I can just seek immediately in the file to the 5,000th line and read that image out. Now you'd say, well, why is that a big deal? Even if you have 500,000 images and 100 characters per line, you know, that you should still be able to fit that in the memory of the computer. And it's true, yes, on a modern computer now, yes, you could fit a 500,000 particle project, but you'd be eating up 500 megabytes of memory to hold that whole thing in memory. And if you have several different variants, then that's another 500 megabytes. And anyway, it's just not a very efficient way of handling things. So we like to have a mechanism where we can keep the stuff on disk. So if you have a project with 5 million particles, it'll also work with 5 million particles. So these LSX files provide a mechanism for that. But historically, they didn't provide a mechanism that we would use, put metadata in the files. It was basically just a pointer to another file. So we have now, in these newer LST files, we've started supporting metadata in the headers as well. So now if you look at, SPT 37 and one of these ALI particles files, again, it's particle number, file name, but then there's a tab, and then there's a dictionary. And the dictionary allows you to specify additional metadata, which will override the metadata stored in the original image object. So this gives you the
So they're not stuck at some static length. It's just whatever the longest line is, I'm guessing.
So yeah, right. So when you generate the file, it goes back and it processes it. So it picks the correct line length for the file. Yeah. Okay. There's a normalized operation which will go back and rewrite the file that way. The assumption is that you're going to be reading this file a lot more than you're writing to it. So the normalization operation is something that doesn't have to happen. So you can write 1,000 lines to the file, and then at the very end it just does one pass and figures out what the longest line was and rewrites it. So the file is still valid if you don't have an even number of the same line length, but then it's an LST file instead of an LSX file. They're both understood by Python, and they both use the same extension. But if it's written as LSX, then it has this characteristic. So anyway, so this is the new mechanism that we're sort of moving to in the future. So there's a human readable file which contains all of the relevant header data that's changing all the time. All the sort of fixed header data, which doesn't ever change, is still stored in the header object of the original image. And from a programming perspective, it's completely transparent. If you read from this LSX file, it will read the original header, and then it will overwrite any of the header information with information that's stored in this file. So you have a nice, easy to manipulate text file. Obviously, if you're going to manipulate, if you're going to change the length of the maximum line, then you'd have to sort of go back and renormalize it. But there's a command line utility you can use to do that, or you can use the Python object, which is LSX file. So there's an object LSX file which allows you to automatically handle all of this writing and extra dictionary stuff and that sort of thing. So we considered for a while just going with star files for this purpose. And we are planning to still support in EMAN2 direct reading of star files in a similar kind of way. But really, since we lose this mechanism to sort of quickly seek inside the file, we felt that was too big a price to pay. And there's also other issues with star files. Since star files have to have exactly the same metadata for every particle, that adds extra headaches. So this, you don't have to have the same metadata for every particle. If you wanted to have different metadata for even particles and odd particles or something like that, you can do that freely. Every line is independent. It's more or less it's basically the star files are a relational database, and this is an object-oriented database in a certain sense. You can manipulate these LSX files. You can treat the LSX file as an image file directly and just read from it. Or if you want to manipulate the specific metadata in the LST file directly, then you create one of these LSX file instances. So we'll call it Z equals LSX file test.lst, like that. And now I can do things like Z of 0 is equal to, I have to get the order right, though I don't do this very often, x.mrc, and then I could put some extra metadata in, like that. Oops. And just to make sure, it actually shouldn't be necessary, but I'm just being extra careful. Oh, sorry, I'm in the wrong folder again. So now you can see we have a test.lst, and it's properly formatted. It has the correct reference to the correct image and everything like that. So there are various, if you ask for help on these LSX files, it'll tell you what it supports. It's fairly straightforward. I mean, there's nothing magic in here or anything like that. It's just a few things for reading and writing these conveniently.
So how do you decide when to use the list file and when to use the JSON file?
So what we're moving to in the next version of EMAN is that these LST files are going to be used basically for all of the, anytime you're running a refinement or anything like that, anytime you have sort of metadata that's going to change in every iteration or something like that, that's going to go in one of these LST files. The JSON file is storing generic information for like an entire micrograph, right? So it doesn't just apply to that micrograph, it also applies to all the particles that are from that micrograph and everything like that. So they're sort of a higher level of information. I mean, that's basically it. So we won't be using the JSON files. We had a brief period where we were using the JSON files kind of like LST files for some of the, we've had sort of 3 different versions of the tomography pipeline. We had a version from like 10, 12 years ago, which just did 3D alignments. Then we came out with a sort of a first draft of the newer variant of the subtomogram averaging, and that made use of JSON files briefly. And then this new format, which does the per particle per tilt alignment and subtomogram averaging stuff and can do sub-nanometer resolution, that now all uses these LST files. Same thing for single particle analysis. We have a new single particle analysis pipeline that doesn't make class averages or anything like that. It's a more straightforward protocol, and it makes LST files for every iteration. There is actually also a star file object, which can be used to do basic star file reading. So if you have an MRC star file and you want to read the metadata out of it to do something with it or something like that, there's a basic star file object, but it's not super featureful at this point in time. And I think that's called star file. Maybe it's all caps or something. Let's try it. Oh, you actually no. I think you have to import it separately. When you import EMAN2, you don't get the star file by default. Sorry, I haven't used this in a long time. No, I'd have to. I'll next week. I'll mention the star file. I don't remember. Yeah, we've been going for an hour and 10 minutes now. Any other questions about this really basic sorts of stuff? I mean, next time we can get into some slightly deeper sorts of things, but it's important to cover some of these basics about reading and writing images. So, if you want to go into Python and read convert from one format to another, it's as easy as doing a read image and then a write image, right? Just do a read image from the format you want, whatever format you want, and do a write image to whatever format you want, and you're done. Most of the header stuff should be preserved fine. And as I said, if there's something in the header that isn't getting preserved in a way that you like, that's something that's really easy for us to update. So just let us know.
I do have a slightly technical question.
Sure.
How do I call from a Python script, basically? How do I call EMAN2 if it's installed in Conda? Do I have to activate Conda first, the Conda environment? Or is there a way to just grab the Python libraries?
Yeah, you have the Anaconda environment has to be active for you to use EMAN2 Python scripts, basically, yeah. Otherwise you won't get all the right dependencies and stuff. I mean, that's really why we use Anaconda now for distribution, right? We used to do it the old traditional way, which was, well, try and rely on the system libraries and make sure you've got compatible system libraries installed on the machine. And if you don't, well, then you install other versions of the system libraries in your home directory and use LD library path to point to the right folder and that sort of thing. But then you've just got this humongous logistics mess. And then people are writing their own commands, activate EMAN2, activate Spider, activate rely on, which would then change their shell variables to make. Anyway, Anaconda just is basically a simplification of that process. So yeah, you have to have Anaconda activated to call EMAN2 scripts.
Okay.
Okay. If there's no other questions, I think we'll just stop for the day. And then next week, go a little deeper into some things that you can do with EMData objects and manipulate them, how to manipulate them. All right.
Thank you very much.
Hi, everyone.